Okay, so this is an attempt at an explicit calculation, uh, basically using the formulas that I've already obtained in my CAN structured sets explicitly videos to work out a specific problem. And it's basically working out the CAN extension of a dynamical system t in set to the power of, well, let's say the right CAN extension of a dynamical system t in set to the power of m along this functor k from m to c. Okay, so basically here's c. I mean, this isn't really a monomorphism, but if it was, it'd be like this, and then we've got, here's t, that sends us to set, that sends this stuff to set, and then we want to sort of extend it to get this functor, which is the right CAN extension of t along k, where k is kind of like, well, this is functor from m to c. But anyway, we'll talk about that soon. It's very interesting, actually. Yeah, so let's just get to it. So this functor k is a functor from this index category for dynamical systems to itself, or we could say m equals c equals the free monoid with one generator. And the way this stuff works is it sends sigma to the power, k sends sigma to the power of n to sigma to the power of 2n. Of course, it sends the only object in m to the only object in c. So basically, then a set to the power of k, it's going to be sending a dynamical system, say v in set to the power of c, to basically the same dynamical system. So say that this is, well, let's write it a bit more. So it's v with, well, so okay, we could write it a bit more explicitly. This dynamical system, it has state set v star, an update function v sigma, and this gets sent to v star, but with the update function v of sigma squared, or v of sigma after v of sigma. So basically, it set to the power of k kind of speeds up a dynamical system. It double speeds it. And so it's quite interesting, really, because, I mean, we've got this kind of situation. We've got set to the power of k, then set to the power of c to set to the power of m, and then we want to get, oh golly, I've done that the wrong way around. Right, so it goes like this. That's better. That's set to the power of k, then set to the power of c to set to the power of m. Now its right adjoint is rank k. So set to the power of k basically double speeds a dynamical system. And so what's its right adjoint do? Well, interestingly, it sort of half speeds a dynamical system. And seeing how that works is quite fascinating. It's another one of those lovely situations where we're really seeing the kind of direct way that stuff like this is defined. So yeah. So yeah, this is how k is defined. Now, okay, let's just go ahead then, and we want to calculate ran k. So we'll start by calculating how ran k works on objects. So say we have an object t in set to the power of m. We want to work out r is equal to ran k of t. Okay. So we only have one object, c, in our category, capital C. So this comma category C downwards arrow k is going to be star downwards arrow k. And basically it looks like this. Okay. So the objects have the form star. Where is it? Yeah, the objects have the form star comma sigma m for m greater than or equal to 0. And an arrow from this kind of object to this kind of object is going to be something like sigma to the power of k, where we have the property that n is equal to m plus 2k. All right, so we have this kind of situation. Basically, the comma category looks like two kind of copies of this linear partial order, I suppose. And so now we just apply the formulas to work out the form of r of c. So t is a functor from m to set. Firstly, let's form this big product. So S is the product of over all of the objects in this comma category of T of M. Well, M is always star. And basically the objects in the comma category are all sort of sequentially labeled. Sigma 1, sigma 2, sigma 0, sigma 1, sigma 2, sigma 3, and so on. So basically, S is just T star to the power of infinity, or the set of infinite lists of elements from T star. But we don't want to select all of those. We want to cut them down. So this is the sort of formal way of describing R of C or R of star. But I think we can simplify it. So we can say that basically R of C is the set of infinite sequences which have the property that given any element in the sequence, so the elements are all from T star, and given any element from the sequence, let's say that mth element, well then the m plus 2th element will be obtained by updating that. So that just means that we can just select the first two elements. So basically these things in R star are always going to have this kind of form. It's going to be TA, comma TB, and TA and TB are going to be any couple of elements from T star. And after that, we're going to have, I need a new symbol, mu of TA, and then mu of TB, and then mu squared of TA, and then mu squared of TB, and then mu cubed of TA, and so on. So basically all the information is really just held in the first two elements. And here mu is T of sigma. Okay. So if we define, so we could say that this is the set of all psi of TA comma TB for a couple of elements TA, TB in T star, where psi of TA comma TB is an infinite sequence of values from T. In the even entries, So say the 2v entry is obtained by applying the updates mu basically v times to ta, and the 2v plus 1 entry is obtained by applying the update v times to tv. So it's fascinating actually because, well, yeah, anyway, so this is what a state of the system looks like. What's the update? So yeah, we're after this can extension. I've already kind of said that. And we're aiming for this R at the moment. I've already said how R works on objects. How's R work on arrows though? Again, we can get this by pulling out our results from before. So there's only really one kind of arrow that we're interested in. So it's this arrow sigma from star to star in C. And we want to find out R of sigma. And basically just by looking at the formulas, we can see that it's what R of sigma is going to do is it's going to shift the sequence one step to the left. Okay, so I think this is beautiful. Because how does this work? Well, basically, if we have any element t in R of star, we can always write it as psi of ta comma tb, and now R of sigma is going to shift that one to the left. So now the first two entries in this list are going to be tb comma t of sigma of t of a, and so we've shifted that sequence one step to the left. And here's one interesting thing is that if we do two of these updates with R of theta, then it sends this to this, which is kind of like doing one update in the original system. So basically, whereas set to the power of k sends a system to its double speed dynamical system, this ran k, which is the right adjoint of set to the power of k, sends a dynamical system to its half speed dynamical system. And so this is the case where little r is 2, where our multiplier, our speed multiplier, if you like, is 2. But we could consider a more general case where it's little r. And then yeah, so it starts to get a little bit fuzzy, but there seems to be something like a sort of conservation principle here. So like when we had that 2 case, we found that our sort of observation window, or the sort of length of the thing that we're looking at, is now 2. So in a way, it takes twice as long for it to update, but there's like twice as much uncertainty in what's going on because it's all sort of blurred out. Or I suppose we could say, it's interesting, we could say that in a sense, if these are different values in here, then in this case we have 2 values, so we could look at the average of them. So in a sense, we're getting twice as much resolution on this. So if we make the time window smaller, then we have less uncertainty in the kind of state of the system, because in this kind of scenario we see 2 states, and therefore we can kind of take an average of them to get a more to get a sort of higher resolution guess at what's going on. So anyway, another way, so what I'm saying here basically is that it looks like we're getting something like the Heisenberg uncertainty principle here. Okay, so I'm sort of reaching for it in different ways, and I'm not quite sure if I've got it yet, but it looks like there's something there. Another way of looking at it is that this R is really giving us a length of an observation window. So we can think about it as an uncertainty level in states. And maybe the update speed can be considered an uncertainty in momentum. So we've got delta x times delta p. And so our observation window is like our uncertainty in state is like R, and our update speed is like 1 over the number of updates it takes in the new system, in the slower system, to do the original thing, which is like 1 over R, which is like the uncertainty of momentum in some sense. So this all needs some more thought, but it seems very interesting that there are these kind of connections here.